Welcome back everybody, Gary Simmons here for the Game Institute. Now in the last lesson we baked ourselves this navigation mesh and we also placed 6 waypoints in the scene. Now these waypoints were just empty game objects, but we get them showing up in the scene view as these little blue flags. And hopefully you will recall that we can do that quite easily by selecting the game object and in the top left corner of its inspector assigning it a custom icon. And of course we can either do that by choosing one of the ones that Unity provides us with, or by clicking the other button and choosing one of the textures that's been imported into our project. Now you'll also recall that the waypoints that we defined, we also parented them to a top level container game object, which I called waypoints. And the reason I do that is in a proper game level, which is usually much bigger than this, we often have many waypoints defined. And this can really clog up your hierarchy view and make it really slow you down if you're trying to always scroll past dozens or hundreds of objects each time just to get to the one that you're looking for. So the idea being is that when we don't need to inspect the waypoints at this level, we simply close up the top level object and our hierarchy view becomes a lot less cluttered. Now the waypoints have been placed in the scene, but we also needed a way to define the order in which our agents are going to visit these waypoints. And we came up with the idea of a waypoint network. In the scene you can see we created 2 waypoint networks, and a waypoint network is really just a game object with this AI waypoint network script assigned to it. And this component, you will remember, was just really a list of transforms. And the idea is that we can drag this pool of waypoints into a waypoint network in different orders so that we create different paths, so that when we have multiple agents in the scene, we can assign them all different paths from the same pool of waypoints, and we don't have a situation where all of our agents are all moving between the waypoints in exactly the same order, because that would look really stupid. Now the problem we have at the moment is, although we can see the waypoints, when we select a waypoint network we get no feedback whatsoever from the scene view as to how that network has been defined. It would be much nicer if when we selected one of our waypoint networks we could see little labels next to the flags which told us the order in which that waypoint is stored in the network. Or even better, if we could have lines showing their connectivity so that we could see at a glance the order in which an agent that was assigned this network would visit the waypoints. In fact, wouldn't it be great if there was a way that when we were positioning our waypoints we could even see how that would influence the A-star search and the path that would be generated on the nav mesh? So that's what we're going to do in this lesson, or at least in the first part of this lesson. We're going to write an editor script that is going to completely override how our AI waypoint network is rendered in the scene view. And we're also going to write a custom inspector, a very simple one, but a custom inspector for our AI waypoint network as well, that will allow us to choose between different modes of rendering in the scene view. So what I'm going to do now is I'm going to pause the video, I'm going to add some code, just temporarily, so that I can show you what it is we're actually going to build in the first part of this lesson. Okay, I'm back. That was quick, wasn't it? And let's see what happens now if I select waypoint network 1 from the hierarchy view. First of all, notice in the scene view we now get these little labels next to each flag so that we can see clearly the order in which these waypoints are defined. We can see that the first waypoint is here, waypoint 0. And these lines also show us the order in which the agent is going to visit these waypoints. So we can see in the case of network 1 it's going to go from here to here, then from here to here, and back. And if I choose waypoint network 2, where the waypoints have been added in a completely different order, we can see that waypoint 0 is here, then it's going to go over there, then here, then all the way back to this room in the bottom left corner, then all the way over here to waypoint 4, then back to waypoint 5. Also notice that the inspector now looks different. We still have the list like we had before, but now we have this little display mode, and it's currently set to connections. In other words, it's showing us how the waypoints in this network are connected to one another. But of course, this doesn't show us the path that the agent following this network is actually going to take. For example, when moving from waypoint 0 to waypoint 1 using this network, it's not going to go in a straight line like that, because that would mean it would walk straight through a wall. It's going to sort of go around the outside here. So what I've also done is another display mode for the network, which we can choose, not connections. This is now called paths. So if you look in the inspector now, you'll notice that for our AI waypoint network, when we choose the paths mode, we now have two sliders that we can use to choose the two waypoints that we want to see the path between. So I'm going to choose, I'll start off simple. I'll just choose waypoint 0 and waypoint 1 of this waypoint network. And we can see that the path that would actually be taken would be to go around the outside of this room here and then in through the door. So this is really useful when you're placing different waypoints, because you can choose whether you're placing it in the correct place to get the path that you actually want. So to give you an example, I'm going to lock the inspector of the waypoint network so that when I select a waypoint to move it, the waypoint network inspector still keeps focus, and therefore we still get these lines rendered in the scene view. Just to show you, if I didn't do that and then I selected a waypoint, I now lose the lines because the waypoint network hasn't got the focus. So I'm going to lock the inspector by using this little padlock up here in the top right corner of the inspector, and then when I select any of these waypoints, although I see their transform gizmos, I still get my custom drawing in the scene view. So I'm going to select waypoint 2 over here, and then I'm going to move it around, and you see that as I move it around in real time, we see the path being generated for it. And we can see the path change as we move it about. And you'll also see that if I do something like move it on top of the battle bus, the path disappears completely, because what I've done is I've moved the target waypoint inside a solid object. So what's happening when we query the nav mesh, it's saying that no path can be found. We're getting no path back. So pretty cool tool, I think. So this is going to be a really good way for us when we're placing our waypoints to just make sure that our waypoint placement is going to generate the exact path that we want. But like I said, there's two different modes that we can put the network in with respect to scene view rendering, and this one is pretty useful, the one that just shows the order in which these are connected. So you just get a very quick preview of the route that the AI agent is going to take. So in order to show you how this is done, we're going to have to talk a little bit first about how editor scripting works in Unity. So let's do that now. Okay, so I've now rolled the project back again, so it's now in the state it was in at the end of the previous video. So when we select a game object in Unity's hierarchy view, that game object is going to contain one or more components. Now, when I say components, I'm not just referring to Unity's built-in components, such as the transform component or a camera component. I'm also talking about our own scripts, our own behaviors, such as the AI waypoint network component. Now, each component on a game object, when it's selected, is given the opportunity to render itself in the various windows of the Unity editor workspace. So we get a chance to represent ourselves in the scene view. So in the case of a transform component, when given this opportunity, it renders the transformation handle that we're used to seeing on all of the game objects in our scene. And that's why when we add an empty game object to the scene, it still shows up in the scene view, because every game object has a transform component. And the transform component will check with the editor to see whether it's in translation, rotation, or scale mode, and it will render the correct handle depending on the result. Now, in the case of our own scripts, such as our AI waypoint network script, because we haven't provided our own custom editor script, the default scene view behavior is to render nothing at all. That's why when we select our waypoint network, all we see rendered is just the transformation handle, and that's the transform component responsible for rendering itself. So every component gets a chance to render something in the scene view. Of course, the other window where rendering has to happen on a per component basis is in the inspector window, where each component will have a chance to render its controls. Now we can see, for example, just with our very basic waypoint network, which has two components, that the transform component lays out its controls very differently to that of our AI waypoint network component. Now in the case of our own behaviors where we don't provide a custom editor experience, Unity will draw a default inspector for us. Of course, it understands what all of the various data types that are being serialized to it are, things such as ints, floats, arrays, strings, enumerations, and in our case a generic list of transforms, and does a pretty good job of choosing the correct control types to display them to us and make them interactive. So for our list of waypoints, it uses this sort of array structure where each element gets given an object box that we can drag and drop references into. And that's normally fine, but when you start creating quite complex components, they can have lots and lots of data, and all of a sudden, just using Unity's default layout can become very cluttered and confusing to use. And it's in those situations that it's nice to write a custom inspector so that you can simplify the interface and just make it feel more professional and more intuitive to work with. There are also other places that we're not going to cover in this lesson where you can also override the functionality of the rendering, such as if we select my prefabs folder in the standard assets folder and select any of the prefabs in there, you can see we also have this preview window. That too can also be overridden, so you can render your own custom previews. We can see that the prefab preview looks quite different to that if we select a material. Preview window is still there, just behaves in a completely different way. And pretty much all the core windows that comprise the Unity Editor workspace can be customized to some degree so that you can really create a very cool looking tool set for your game. Now we're just going to concentrate in this lesson on customizing the scene view representation and writing a custom inspector for our waypoint network component. Okay, so what we're going to do now is create a brand new C# script that is going to contain our custom editor behavior. However, what is really important when writing an editor script is it has to be placed inside a folder called editor with a capital E, like so. If it's not, Unity won't recognize it as an editor script and it won't do its intended job. Now, it doesn't matter where this editor script is located in your project hierarchy. In fact, you can have multiple editor scripts spread throughout your project. Unity treats them as if they're essentially all just one big folder. In fact, if I close down my dead earth folder and step up into my root assets folder, you'll see another editor folder exists there. Now that wasn't created by us, that was created by Unity when we imported some of those asset packages, some of Unity's standard assets, and that's obviously because some of those assets have a custom editor script. In this particular case, it's the cross-platform input component, which obviously has a editor script that is called cross-platform input initialize. So like I said, you can have multiple editor scripts, but in my case I'm going to place all my editor scripts in the editor folder that I've created underneath the dead earth folder, and that way I know that that's where all of the scripts that I'm responsible for are located. So let's go to the project view, right click and do create new C# script. Now, when naming the script, we don't have to call it anything special to relate it to the object that it's going to do custom drawing for, but I like to use that kind of naming convention anyway. So because I'm basically creating custom editor functionality for my AI Waypoint Network class, I like to call the editor script AI Waypoint Network, but then put editor on the end of it, like so. So then it's very easy for me to see which actual component this is an editor script for. So let's open that up. So the first thing we're going to do is we're going to get rid of the boilerplate stuff, because actually the start and update functions are only applicable to mono behaviors, and this script is not going to be derived from a mono behavior. Instead, it's going to be derived from a class called editor. However, we don't have access to just the editor class and its functions because it's inside the Unity editor namespace, which isn't sort of included by default. So rather than have to put Unity editor before everything and specify the fully qualified path every time, we'll just say using Unity editor like so. And then we'll delete mono behavior And we'll say that this class is to be derived from editor. And you'll see in a moment that the editor class is kind of the editor equivalent of the mono-behavior class for runtime scripting. It contains functions such as onInspector GUI and onScene GUI that we can override and implement to change the way that the inspector is rendered and the scene view is rendered. However, at the moment we have created a editor script. Okay, it doesn't do anything, but we have created an editor script. But Unity doesn't know at the moment what component this editor script is supposed to be for. Now we know that when an AI waypoint network component is to be displayed, this is the script that should be used, but Unity doesn't know that, so we have to use an attribute above the class to tell it that. We use the custom editor attribute. So open square bracket, custom editor, like so. And inside the parentheses we put the type of the object that we would like this editor script to be used to render. So we know that the type of object we'd like this to be used for is when rendering objects of type AI waypoint network. So we do type of AI waypoint network, like so. So now, because we've said this is a custom editor class and it's supposed to be intended to override the behavior of any AI waypoint network component, Unity has everything it needs to associate this editor script with the runtime component. So let me save that off, just check we haven't got any errors. All is fine. So now that we have our custom editor class, all we have to do now is go and look up the editor class in the scripting reference of Unity's manual so that we can see which functions we need to implement to override the various behaviors. So let's do that now. I'm going to go to the Unity scripting reference, and because we're looking at classes that are in the Unity editor namespace, we look in there instead of Unity engine, which is where our mono behavior stuff normally is, and we look under classes, and if you scroll down you'll see that there is the editor class. And if we scroll down we'll see a list of all of the variables and all of the various functions that are provided to us that are either functions that we can use to do something, or in the case of the functions that start with on, those are the functions that we can implement. So you can see there's the onInspector GUI, and that's the function that we'll implement when we wish to override the way that controls are rendered in the inspector. There's also the onPreview GUI, which is something that you could use if you wanted to override how the preview of the object is drawn in the preview window. And if we scroll down, there's also the onScene GUI function, and that's the one we're going to implement first, and that's the function that's going to be called by Unity when it's time for our object to render itself in the scene view. So let's have a look at that. And let's implement that now in our script. Like so. So inside this function we're going to start off really simple, and all we're going to do is we're going to loop through each of the waypoints in the network, and we're going to put a little label up above it in 3D space that says something like waypoint 0, waypoint 1, waypoint 2, and so on. So the first thing we need to know is, now we're inside this onScene GUI function, we need to get access to the waypoints inside the associated AI waypoint network that is currently selected. So how do we do that? How do we get access to those waypoints from within this editor script? Well, fortunately, if we go back to the scripting reference again, and once again back to the variable list of the editor class, you will see there is this variable called target. And this is an object reference which will automatically be populated with a reference to the selected component. So this is the reference to the AI waypoint network that has the data we want. So in order to get the waypoints from it, all we have to do is use this target member, cast it to an AI waypoint network type, and then we can just work with it as normal. So let's do that now. So I'm going to create a local variable of type AI waypoint network, and I'm going to call this variable network, and I'm going to assign it that target reference but cast to an AI waypoint network, like so. So now, using this network reference, we can now access our waypoints by just going network.waypoints. So if I wanted to loop through all of the waypoints in the waypoint network, I could simply set up a for loop like so. As you can see, we set up a for loop that says for I equals 0 at the start, it keeps looping until we've reached the count of the waypoints that are inside our AI waypoint network. So for each iteration, we're going to be visiting a different waypoint. So all we have to do is fetch the waypoint at the respective index and then draw a label for it. So we know the position in 3D space of the waypoint because that's actually contained in the waypoint itself. Remember, each of our waypoints is actually a transform component. So for each waypoint, once we fetched it, we know it has that position property, which is its position in 3D space. But how do we actually render some text in the scene view in world space? Well, fortunately, going back to the scripting reference again, Unity provides us with the handles class. I'll select it here. And the handles class provides us with a myriad of functions to draw all sorts of complex interaction mechanisms. It's using this that you could create your own translation and rotation gizmos, your own scaling gizmos, but all we want right now is we just want to use the label method, which is the most simple of them all. We just provide it with a 3D position in world space and a line of text, and it will output that text in the scene view at the past world space position. So let's do that now. So we will say handles.label, and for the position we simply just fetch the position of the current waypoint that we're processing from the AI waypoint network, like so. And for the text, what we'll do is we'll say waypoint, and then we'll add on to that the loop variable I toString, like so. And now when we go back to the editor, assuming we have no errors, when we select one of our AI waypoint networks, hey, look at that. We have now rendered in 3D space some text above each waypoint in the scene view. So we can already see now, just by selecting our different AI waypoint networks, the order in which those networks are going to be visited or are stored in its internal arrays. So that's a pretty good start. Now, one of the things we should probably do is we should probably put a check in there that just makes sure that the waypoint isn't null, that we have actually assigned it something. So I'll put a check in there. Otherwise, we're going to get a, we're going to get an error when we try and access a waypoint that is null. So we say if the network waypoint isn't null, then output that position. But if it is null, then we'll simply skip over it. There's nothing we can do. So let me save that off. Just check we have no errors. And no, we don't. Okay, I've just noticed that I meant to leave a space between waypoint and the index number. So if I go back to the script again, I'm just going to insert that space in there, save it off, and just check. Yep, okay, that's cool. So not a bad start. We're certainly getting some more visual feedback. But what I want to do now is take it a step further, and I want to connect the waypoints together in sequence so I can see, if not the exact path the agent's going to take, I can at least see more clearly the waypoints that are going to be visited by the agent and in what order. So we're going to need to find a method that will allow us to draw multiple lines between all of our waypoints. So if I go back to the Unity scripting reference and look at the handles class again, you'll see that there's actually a function here called drawPolyLine. Sounds exactly what we need. If you look at the function, we simply pass it an array of vector 3s, in other words, an array of 3D space positions, and it will automatically draw lines between all of the points that we send it. Now, although we have 6 waypoints, we're actually going to pass in 7 points, where the very last point in this array is going to be a duplicate of the first point in the array. And the reason why I'm doing this is I want one additional line that is going to connect the final point back to the first point. Okay, so let's implement that now. Let's go back to our editor script, and the first thing we're going to need to do is we're going to need to allocate some space to store that array of vectors that we're going to collect. So as you can see, I've called this line points. It's an array of vector 3s. And the number of points I want to allocate is going to be the size of our waypoint network plus that additional point to store a duplicate of the first waypoint. So as you can see, I've allocated the number of vector 3s equal to number of waypoints plus 1. Now what we need to do is we need to loop through our waypoints again and collect each of the waypoint positions and add them to this vector3 array. So what I've done this time is, rather than loop from 0 to number of waypoints minus 1, I've actually said keep going while I is smaller or equal to the waypoint count. Now remember, because our lists are essentially stored in a 0-based indexing scheme, this is basically equivalent to saying I want you to do one more iteration than there are waypoints. So inside the loop we need to calculate the index of the waypoint that we need to fetch. Now for most iterations of the loop the index will simply be I, but in the last iteration of the loop, when I is equal to the waypoint count, that means we've gone past the end of the waypoints and we wish to sort of fetch the first waypoint in the list again. So let's do that now. So as you can see, I've created an integer variable called index, which I'm going to use to index into the waypoints array. Now we know that we've got 6 waypoints in our array, which means that valid array indices are actually 0 to 5. So in the case where I is smaller than 6, the number of waypoints we have on our count, that is a valid array index. So we simply set index to the value of loop variable I. But in the case where I actually equals, say, 6 in our case, well, we know that's not a valid index for an array that has 6 elements, because the indices of a 6-element array actually go from 0 to 5. So the minute that I equals 6, in our particular example, we know that we have stepped past the final waypoint in the array, and we want the next index to be the first index in the array again. Remember, as the very last waypoint, we want to fetch the first waypoint again. So that's what this line does here. Then we're going to say, assuming that the waypoint stored at this index isn't null, it's a valid index, so we will add the position of this waypoint to our line points array. So you can see we're essentially using that index to fetch what the next waypoint in this list of line points should be, and just copying it into our line points array, assuming of course it isn't a null reference, because there's nothing we can really do about that. In fact, what I will do about that is I'm going to say that if it is null, and that, that's very possible, we could have forgotten to assign a reference to it, then we'll set the line point to some crazy position like a vector3 where every component is sort of mathf infinity or whatever. So that way, if we do leave one of our waypoint slots unassigned, the lines in the scene view will go crazy and we'll be able to see very easily that we've got a problem. As you can see, in that particular instance, we just assign to the line points a new vector where each component is math affinity, the largest number that can fit into a float. So that's going to send that line in some crazy direction in our scene. Okay, so at this point, outside of this loop, we've now collected all of the waypoints that we wish to draw lines for, and they're all stored in our line points array. So what we have to do now is call that handles draw polyline function and pass it our line points, and it should draw our lines in the scene view like so. So let's save that off, and hopefully we haven't got any errors, but I have. What have I done wrong here? Now line points is a vector3 array and waypoints is a transform, so that should have been waypoints index dot position. What am I like? Okay, let's try that. Hey, there you go. We're now seeing the connectivity between our waypoints, and we can see quite easily just at a glance that we go from waypoint 0 to waypoint 1, from waypoint 1 to waypoint 2, and we can just see the path that, or at least the rough path that our agent is going to take. But of course, this isn't doing any A-star searches on the nav mesh. This is just the raw connectivity. But most of the time, I actually have it in this mode because that's all I need to see. I also want to change the color of those lines. I don't like them being white. I want them to be kind of a similar color to the flags, that cyan color. And we can do that really easily. Before we call the draw polyline function, the handles class has a color property. So I'm just going to say handles.color equals color, and I'll just choose color.cyan, like so. I save that off. Our lines should be cyan now. There you go. So it stands out a little bit more, doesn't it? So when we saw the demonstration of what we were going to create a moment ago, you'll remember that I actually implemented two modes. I also had a paths mode which allowed us to select any two waypoints, and then we could actually see the path that would be generated on the nav mesh, the actual path that our agent would follow. So we're going to implement that now, and in order to do that we need to store some additional information in our AI waypoint network so that the settings we choose for each network is remembered. So you will remember one of the things that we had was a little drop down bar that allowed us to choose between connections mode, which is what we see at the moment, and paths mode, which was the one that actually showed the route that was generated on the nav mesh. So we're going to create an enumeration in our AI waypoint network script to define those different options. So let's open up the AI waypoint network script, and I'm going to add a public enum called path display mode, and the options, actually I'm going to add 3 options. I know my demo just now only had 2 options, but I'm also going to add a none option, alright, just so we can just turn off all rendering of this object in the scene view. So we're going to have none connections, which is the mode we currently support, and paths. And I'm also going to need to create a member of this type in the class. So we're going to say public, and I'll call this display mode, and we'll set it to, I think the default will be connections mode, the one we've got it in at the moment. We save that off now and go back to the editor. You'll be able to see in our inspector, if we select our waypoint network, we now have this little drop down which is on connections by default. Now obviously if we select any of the other modes, they don't do anything at the moment. We're just toggling the various values of an enumeration, but it's actually going to be our editor script now which is going to fetch this mode from our AI waypoint network and render the scene view accordingly. So we want to go back to our editor script, and at the start of our on-scene GUI we had this for loop that basically rendered all the labels. Now we want that to happen irrespective of the mode we're in. Okay, so we'll leave this as it is, but this bottom section of the code is where we drew the polyline joining up all of the connections. So that is going to be our connections mode. So we're going to need to surround that in a conditional so it only gets executed if the AI waypoint network is in connections mode. So we say if network.displayMode equals path display mode.connections, and then we wrap all of that code in a conditional. And what we'll also do just underneath it is we'll say else, and we'll do the other conditional, even though we don't know the code we're going to put in it yet, for when we are in paths mode, like so. And I'll just leave that conditional empty. So if we save that off, go back to the editor, check we haven't got any errors, we can see now that if we select none, the lines disappear, but we still get our labels. If we put the network into connections mode, we see the lines. And if we choose paths mode, it just looks like we're in the none mode, okay, because we haven't implemented that paths mode yet. But the great thing is that because we stored the path display mode in the actual AI waypoint network, it means it gets serialized with the object along with the rest of the data, and therefore Unity will automatically remember that we might have AI waypoint network 2 set to none, but AI waypoint network 1 set to connections. Now the other way that you could do this would be to actually store the connection mode as a member of the actual editor script, but if you do that, when you switch between objects, that instance of the editor script essentially loses focus and its data gets reset. So I always like to store the actual data that I want to be remembered in the actual component that we're rendering, and have the editor script really just fetch that data and allow us to modify it. Now in order to implement the paths mode, and I'll put it in paths mode now, you will remember that we had 2 slide bars that allowed us to select a start and an end waypoint, and then it would query the nav mesh and show us the returned path in the scene view. Now the reason I don't just show all of the paths on the nav mesh is that nav mesh lookups are quite expensive, so we want our editor environment to be nice and interactive. So we don't really want to be showing the paths and doing navmesh queries repeatedly, unless we're really trying to diagnose the route between two waypoints, or if we're placing a waypoint and we want to make sure we've placed it correctly. So that's why I only allow you to choose two. But there is of course nothing wrong with you modifying this and simply drawing the navmesh paths between all of the waypoints, but that's just not the way I'm going to do it. So just like we added a display mode member to our AI waypoint network, I'm going to do the same thing with the start and end waypoint indices. I'm going to make them integer members of the actual AI waypoint network, not the editor script, and that way that data will once again be serialized along with each object, and each object will remember how we set it. So we're going to open up our AI waypoint network script again, and I'm going to add two more members. I'm going to add public ints UI start, which by default will be set to the first waypoint, and UI end, which by default will be set to, actually I'm going to set them both to 0 because there might not actually be any waypoints assigned yet, so we'll just set them both to 0 to begin with. So if we save that off and then go back to the Unity editor, we can see our inspector has now been updated to show us those two integer number fields. But we saw when we looked at the example a moment ago that we actually had sliders before here, where you can see that the default rendering of this inspector has chosen based on just the type of number it is, and it's an int, so it just shows a numerical int field. So we're going to write a custom inspector a little later on that's going to allow us to make these two sliders and just control how things are laid out in the inspector, but we'll do that in a moment. What we have to do now is we have to implement the conditional code in our on-scene GUI function of our editor script so that we query the navmesh using our UI start and UI endpoints and then render the returned path. So let's do that now. So the first thing we need to do is we need to allocate an object of type navmesh path, because when we query the navmesh, we need to send it an already allocated navmesh path, and then it will populate it with the data we need. So we say navmesh path equals new navmesh path, like so. We also need to fetch the world space positions of the start and the endpoint that we want to query on the navmesh, and we know that the indices of those waypoints are stored in the UI start and UI end members of our network. So let's fetch those now into some local variables. So as you can see, I've got two vectors here. Vector from is the point that we're building the path from, and we fetch that by just fetching the UI start index from our AI waypoint network and use that to index into the list of waypoints in the AI waypoint network. That will return back to us a transform, and we just fetch its position and store a copy of that in this from vector. And of course we do almost exactly the same thing to get the world space position of the destination point on the path, which I've called 2. We just use the UI end member of the AI waypoint network, and we use that to index into the AI waypoint network's waypoint array and take the position of the return transform. So we now have a path that's ready to be populated by Unity, and we have the two positions in world space that we wish to build a path between. Now what we need to do is issue the actual query on the navmesh. Now fortunately, Unity has a static class called navmesh, which makes this incredibly easy to do. And if you look up navmesh in the Unity documentation, you can see that this class is a static class. It's a singleton class, so we know that we can only have one navmesh in the scene, so any functions that we issue to this class is always going to be to the one and only navmesh in the scene. And of course, looking at the static functions, there is a function there called calculate path. So as you can see, this function takes 4 parameters. The first 2 are the source and target positions, which we already have, and the final parameter is a reference to a navmesh path that we've already allocated. So we pass that into the function, and this function will actually populate it with the path data. And as the third parameter, we just specify an int, which is the area mask. And fortunately, the navmesh class actually defines something that allows us to very easily tell it to consider all of the nav areas when doing the search, which is what we're going to do. Otherwise, you have to use this as a bit mask, much like we do when we are talking about other masks, such as culling masks and things like that. So it works exactly the same way. or layer masks. That's the other mask that we often use quite a lot in Unity. So we can go back to our script and we can say navmesh calculate path from to, and then like I said, we have to either specify a bit mask here telling them just the areas that we want them to consider when building the path, or we can just do navmesh.allAreas, which is the only thing I actually care about for now, and then we pass in that path that we allocated. And that's it. When this function returns, that path will contain all of the nodes, or corner points as Unity calls them, that our agent needs to walk along to get from the from position to the to position. So let's just look up the navmesh path in Unity so we can see what members it has. And as you can see, it has two variables. One of them is the status of the path, and the navmesh status just tells us whether the search was complete, whether it was able to partially reach the destination, or whether the path is completely invalid. For example, if one of the points wasn't even located on the navmesh. But the thing we're most interested in is this corners of variable here. And as you can see, this is just a vector-3 array containing all of the world space positions that the agent must head towards in sequence to get from the starting point to the end point. So once we've collected out all of those points, we can literally just draw lines between them all. So let's do that now. So we can use our handles class again, and we can use the draw polyline function again. And this time it's even easier because we already have the array of vector3s. They are just the paths, corners, that were returned from the calculate path function. But what I'm also going to do is I'm going to change the color of the actual navmesh paths to yellow. So I'm going to say handles color equals color.yellow. Save it off, and believe it or not, that should now work. Now I know what you're thinking. You're thinking I can't see anything, but the reason you can't see anything is because at the moment for this selected waypoint network, we've set both the start and the end point to the same position, so no path exists. But let's see what happens. Hey, if we set the end point to 1 or 2 or 3 or 4, or what if we set the start point to 2? Pretty cool, huh? We get to really see the path that is going to be taken by the AI. But I don't like them being text boxes here at the moment, because it's very easy to get errors like this when you're trying to sort of slide around using the default controls, and then you slide the number into negative values. So we're going to make two sliders here that are going to clamp to how many waypoints there actually are, so you can never fill your console up with all of these errors, these argument out of range errors. So in order to do that, we need to write a custom inspector. So how do we write a custom inspector? Fortunately, creating a custom inspector for one of our components is as easy as creating custom scene view drawing, which we've just done. In fact, it works in very much the same way. If we go back to the editor class in the documentation, you will see that there is a function here called onInspectorGUI. Now that's analogous to the onSceneGUI function that we've just implemented, whereas onSceneGUI gets called whenever our component needs to render itself in the scene view. The onInspectorGUI function gets called whenever our component needs to render itself into the inspector. Now this has to be implemented slightly differently, because we saw when using our own components that there is no base class implementation of onSceneGUI. If we don't provide our own onSceneGUI function, it simply doesn't render anything in the scene view. However, we also know for a fact that when we don't provide our own custom onInspectorGUI function, we do see the controls rendered using Unity's default inspector drawing, and that's all contained in the editor class's default implementation of onInspectorGUI. So the long and short of it is when we implement this function in our base class, which is a public void type, we must also make sure that we specify the override modifier. And it says that in the documentation. It says this function has to be overridden in order for this to work. That's our way of saying to Unity, when calling our class, we don't want you to call the base class implementation and do all your usual drawing. We want you to use our drawing method instead. So let's go back to our script now, and let's add an empty function of this type to our script. As you can see, I say public override void on inspector GUI, and this is currently an empty function that does no rendering. So what do you think is going to happen now when I save this off and go back to the editor? As you can see, because we've overridden the default drawing mechanism of the editor class and replaced it with a function that does nothing, we now have a completely empty component in the inspector. And that's expected because we're saying we want to represent the data in this object using our own layout, our own control types. Now, just as the scene view has the handles class to provide us with functions to render things in the scene view, the inspector has the editor GUI, the GUI, and editor GUI layout classes to help us do those same things. Each one of these classes contains a myriad of functions that allow us to very easily render controls of various different types to the inspector. Now, if you've ever used Unity's immediate mode GUI in your runtime behaviors, which was the GUI system that we used before Unity's new retain mode GUI was released in the 4.x cycle, you will remember that there was the on GUI function that we could implement in our mono behaviors, and we also had the GUI class that allowed us to essentially render controls, labels, textures and data to our game window. Well, the editor GUI class and the editor GUI layout class are almost exactly the same as this. In fact, when we're rendering to an inspector, we can even use the same GUI class that we use when we're using the immediate mode GUI at runtime. The only reason the editor GUI and editor GUI layout classes are provided is they give us extra functionality, extra functions to render controls that really are only applicable to editor development. Now, why do we have editor GUI and editor GUI layout? Well, they're essentially the same thing. They provide all the same functionality. The only difference being is that with editor GUI, each function expects you to pass it a rectangle, defining the region in the inspector where you want the control to appear, whereas the editor GUI layout class, which I'm going to use, doesn't do that. It will automatically lay it out for you. So for example, if we want to make a color swatch field, it will automatically stretch it to the width of the inspector and handle all the resizing for us. So that's what I'm going to use. So looking at the editor GUI layout class, you can see that we have functions to very easily render all sorts of control types. For example, we have the color field. And each one of these functions gives you a nice graphical example of what you're going to get. So if we create a color field, we can see we get a label and a color bar, and when we click on that color bar, we see the swatch open up. That allows us to select our color in a very professional way. We also have a mask field, which is very similar to how Unity allows us to provide layer masks and culling masks in its own components. And what we're going to use is a slider. Now there's two sliders. There's the standard slider, which is a float slider, but we're going to use the int slider function. And the int slider function, you can see down the bottom here, is just going to create a nice little slider bar there for us. Now if you've ever done any work with Unity's immediate mode GUI, you're going to be immediately at home with the editor GUI layout class. Basically, all the functions work by taking parameters that define how the control looks, the size of the control, things like that. But it also contains as input the value that you want to set from your component. So in the case of an int slider, we would pass in, if for example this slider was to represent our UI start index, we would pass in as its first parameter our UI start index. But then the value that we get back would also be assigned back to our UI start index. So what we're basically saying when we call this function is we're saying this is the value that it currently is, and you're going to give me back the modified value if it's changed. So we're both passing in the value that we wish to represent and storing the return of the function in that same value. Now if that doesn't make any sense, it will in a moment when I actually do it. So we have a problem at the moment, which is I don't really want to go through the laborious process. Oh, hang on a minute. Let me just comment out that function again so we get the default drawing behavior back. I don't really want to go through the laborious process of having to iterate through all of my waypoints and create an object field for each of these waypoints and worry about resizing the array and all that sort of stuff. Unity does all this for me, and frankly, even if I customized how these waypoints look, it's probably going to look pretty much the same anyway. So I kind of am in a weird situation where I want to use Unity's default behavior for rendering my waypoint list, but I want my UI start and UI end to be overridden so that I can have slider bars there instead that are also confined to valid indice ranges. So what I'm going to do is I'm going to do a little bit of both. I'm going to essentially override the top three members and be responsible for drawing those. But then I'm going to say, after I've rendered these, I want you to draw the rest of it by using the default behavior. And fortunately, this is really easy because the editor class, if I just uncomment that function again, has a function called draw default inspector. So if I save that off now, okay, and then I go back to the editor, even though we're now using our own onInspector GUI function, it's now being rendered exactly the same as before. We're essentially just issuing a call to the base class telling it to draw itself just like it always did. So we know that if we can find a way to stop the default inspector from rendering these top three members and just rendering my waypoints, I can take control of rendering these, and then we can let Unity render those. Well, there is a way that we can do that. So first of all, what we could do is we can open up our AI waypoint network script. And what we can do is we can use a modifier on the top three members and tell Unity that we don't want these displayed in the inspector by using the hide inspector attribute. And I'm going to assign that to the top three members of my class. So what we're telling Unity is that we actually only want it to ever render my list of waypoints. So now if we go back to the editor, and just to remind you, our onInspector GUI function is still being used, but we're just calling that draw default inspector. Now we should only see the waypoints get rendered. There you go. So basically solved one of the problems. I've now got Unity drawing the stuff I want it to draw. All I've got to take care of now is drawing the other stuff that I told Unity not to draw. So that's what we're going to do now. We're going to use methods of the editor GUI layout class to draw some custom controls to the inspector. So let's just go back to our AI waypoint network class, just so we're reminded of the variables that we have to render in the inspector. And the first one is an enumeration. It's a variable of type path display mode. Now, if we go back to the manual and look at editor GUI layout, you can see there's a function here called enum popup, which is specifically for this situation when we wish to show an enumeration in the inspector as a drop-down with all of its various options. So we're going to do that function first of all. So at the top of our inspector, we're going to get that enumeration drop-down. Now, the order in which we call the functions is the order in which they show up in the inspector, okay? So just bear that in mind. Now, the first thing we have to do is exactly the same thing that we do at the top of the OnScene GUI function. We need to get a reference to the actual AI waypoint network that's being edited. So once again, we use the target member of the editor class and cast it back to an AI waypoint network so that we get a reference to the AI waypoint network so we can fetch the display mode. I should mention that if you want your editor script to handle multi-object editing, so for example, if you wanted to be able to select 3 AI waypoint network objects at the same time and adjust their controls, you would need to not use the target member in onInspector GUI, but would instead use the editor class's scriptable object. But I don't need to do that. But if you're writing a complicated editor script, you want to use scriptable object instead. And that's also going to support things like undo and all that sort of stuff. But there's plenty of information in the Unity manual under the editor class that shows you how to do that. But for me, this is just such a simple class, we really don't need multi-object editing or really support for the undo system. So I'm just going to use the target. And the first thing we're going to do is we're going to say network.displayMode equals, and then remember we use that editor GUI layout class, and we're going to use the enum popup function. So we just pass in network.displayMode, like so. Now we're going to get an error when we do this. And the reason we're going to get an error, there you go, an error down the bottom, is because the editor GUI layout enum pop-up function returns a generic object. So we just need to make sure that the result is actually cast back to our very specific enumeration. So we have to cast it back to path display mode, like so. Save it off, go back to the editor. And now we can see that we do indeed have our drop down right at the top of our inspector. I don't actually like that because I actually expected a label to show up on the left hand side, and I've just remembered that I've actually used the wrong version of the function. So if I just press up and down here, you can see that there's another version of the function that takes a label as its first parameter. So I'm going to put display mode like so, comma, then press save and then go back, and oh yes, that looks much nicer, doesn't it? And now we've got our little drop down back, which is cool. Okay, so the next thing I want to do is I want to create those sliders for my my two integer waypoint indices. Remember, UI start and UI end, but we want to represent them as sliders, not as int fields. So, oh, by the way, these scripts will be available in the zip accompanying this lesson. So that will be called Navigation and Pathfinding Part 4. Right, yeah, and you can find that in the resources page of this channel, okay, and you'll also see a link to it under the actual video itself, and I'll also put some nice comments in those scripts as well, tidy them up a little bit, but they'll essentially be exactly the same as this. Okay, so next I'm going to do the network UI start integer. Remember, like I said, these functions can look kind of weird at first because you pass in network display mode, for example, and then the value that's returned is kind of the new position of the slide, or the new value of it, and then we assign it back to the variable that we originally passed in. And this is the same way that Unity's sort of runtime immediate mode GUI works as well. It can take a bit of getting used to, and we're going to do the same here as well. So we want to do an integer slider, so we do editor GUI layout, int slider. And with the integer slider, we can actually pass in, where's the version of the function I want? Yeah, this one here, where we pass in a label, much like we did with display mode. We pass in the value that we wish the slider to be at, which of course is the current value of the UI start member. And we also pass in the sort of the minimum and maximum bounds of this slider. So that's pretty easy. For the label, we will do, we'll do waypoint start. And for the value, we simply pass in network.UI start, and for the bottom range we want 0. 0 must be the smallest indice that they can move this slider to represent, and of course the maximum is simply the count of the waypoints in the list, -1, because remember arrays are 0 based indices. So network.waypoints.count -1, and then we get them both together. So UI end equals editor GUI layout, int slider, waypoint end, and the value we pass in is the current value of UI end. The same bounds apply. See if we get any errors. We now have our sliders showing up. So if I put this into paths mode, we can now see that we've got the ability to select the waypoints. Now you see, if I set both of the waypoints to the same value, no path gets rendered, and that's because when we send the same start and end points into a navmesh path search, it basically finds no path. It just returns immediately. So the reason we're not seeing any line rendered is because we're not getting any corners back from the navmesh. But so it pretty much works. The only thing that doesn't work at the moment is because these two sliders only really apply to when we're in paths mode. They don't do anything in connections mode or in the none mode. We want to hide them when we're not in paths mode, okay? And that's really easy to do. We just wrap this in a conditional. So we will just say if network.displayMode doesn't equal path_displaymode.paths. Sorry, I've done that the wrong way around. I want to say if display mode equals path_displaymode.paths, then wrap that conditional in there. But I've done it wrong, haven't I? I don't want it. I still want the mode selector to show up. It's just the two sliders I don't want to show up if I'd put it where I originally intended to put it, we would have lost the enumeration drop down as well. So there you go. Let's see what that looks like. Well, nothing's changed because we're still in path mode, but you'll see if I put this in connection mode, these two sliders will now disappear because they have no relevance, and the same for the none mode. Put it in paths mode again, and the two sliders come back. So that's pretty cool. So that is actually our custom inspector and our custom scene view renderer taken care of, just like we showed at the beginning of the lesson. Now, there are probably a few things we have to do here just to make this script a little bit safer, because at the moment we're not really doing any tests to make sure that when we select these waypoint indices that there are actually valid transforms stored there. Yeah, we probably need to do some testing here and do nothing if it turns out that when we fetch those waypoints we haven't assigned anything, because there'll be null references, and when we try and access the position of the transform we're going to get errors. So what we're going to say here is basically once we need to check those two waypoints we're just about to fetch. So in other words, we only step into this code if both of the waypoints we fetch doesn't equal null. And there you go. When we set any of those indices to element 1, or in this case 2, you can see we don't get any of those errors, but it doesn't obviously draw the lines either. So cool. So let me just assign waypoint 2 back. And there it is. All works. So the last thing I'm going to do in preparation for the next video is we're going to add a navmesh agent to the scene. We're not going to be able to write the script in this video that makes it traverse the waypoints, because once again time has really rocked on by, but at least we can do a little bit of prep work for it. So I'm going to close up these waypoints now. Okay, so because we're not at the point yet where we've imported any characters or animations, for our agent tests, we're going to need some sort of proxy to represent where a character will hopefully one day be. So we're going to use a cylinder for that. So if you go to the game object menu, go to the 3D object submenu, and choose cylinder. And then we'll just put this somewhere. What height is that? 2 meters? That will do. That's roughly the height of a male, right? Something like that. Well, not me. I'm about 5'6". I could give Walt Davis a run for his money. Okay, so I'm going to remove the capsule collider, and the reason I'm going to do that is because we don't need the capsule collider for our agents anyway, and when we put the navmesh agent component on this game object, it's going to render the agent's radius, which is going to look very much like the cylinder's collider, so we won't be able to tell the difference. But just building on from what we've talked about earlier on in this lesson, obviously if we turn off the mesh renderer, what you're seeing in the scene view is the capsule collider, and from what we've now learned, we know that that's the capsule collider component doing its own bit of on the scene GUI magic to represent itself in the scene view. So I thought that was worthy of mention. And we can make any object or any hierarchy of objects an agent by simply adding the navmesh agent component. So let's not mess about, let's do that now. So with your cylinder, actually let's rename that cylinder, alright? Don't want to call it cylinder, we will call it agent. Bam, 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 bam. Okay, so with the agent selected, in its inspector click add component and type nav, and one of the options you'll be given is navmesh agent. A little sneak preview there of navmesh obstacle, which we'll be using later, but for now we want to add navmesh agent to our object, and you can see that if I turn off the mesh renderer again, the navmesh agent component is drawing its own representation of itself in the scene view, and we can see that it's a cylindrical construct. So we did talk about that earlier, how the agents are essentially represented as cylinders in Unity's navigation system. Now we can see when we look at the top of the properties in the navmesh agent that one of the first things we see is a radius. Now this is really strange, right? Because we saw when we were talking about baking a navmesh that we have no control over the agent at runtime, and in fact we have to bake a very specific agent radius into the navmesh. Well, that's true, and that's not actually what these properties are for, because when we use a nav mesh, that only contains the static geometry, as we've already discussed, but there's also dynamic obstacles, things such as other agents, for example, and they need to avoid each other using a completely different system. And therefore we also need to specify the radius and height of the object here so that the runtime obstacle avoidance knows how much each agent or each dynamic object needs to avoid each other. So that's why we have to specify it in multiple places. But word of caution, do not think that altering the radius or the height here will make any difference whatsoever to the paths that are plotted using the nav mesh, okay? It's not for that, it's just for the dynamic avoidance system. The third property is where we get to specify the base offset, and that's just because sometimes the pivot or center point of the object might not marry up with the navmesh agent representation. So you could have a case where you have a mesh and its feet are on the ground, but it's off center such that the cylinder base isn't touching the floor. So we get a chance to kind of offset the navmesh agent cylinder so that it more correctly matches the mesh that it's going to encompass. Underneath that, you'll see that we have some steering properties. Now the speed is simply the maximum speed that our agent is going to be able to move along a path. The angular speed is the maximum number of degrees per second that our agent is going to be able to change its orientation. So obviously this is going to affect it when it gets to one waypoint and it needs to turn to go on a new path to the next waypoint. This is currently set to 120 degrees per second by default. And we also have the acceleration and stopping distance and auto braking. And these three things are kind of all related. So we don't always just want our agents to essentially leave a given corner point along a path and automatically go at maximum speed. Because in real life, when we walk from one place to the other, we normally ramp up speed a little bit. So the acceleration just allows us to control how fast the agent is going to get up to its maximum speed. And the stopping distance is basically just like a threshold, which basically says if I get within a certain radius of a corner point or a target position, then assume that I've reached there already. It's a little bit like wrapping a bounding sphere around any of the corner points on the path, and when we penetrate that sphere we say, hey, we're basically there. And auto braking is pretty cool, although we're not going to be able to use it unfortunately because we're going to be controlling the speed of our agent using Mechanim. But the auto braking basically just makes the agent more organic. As it starts to approach the corner point along a path, rather than maintain the same speed, it will essentially start to slow down as if it's getting ready to turn onto the next portion of the path. And then underneath that we have the obstacle avoidance, and you can pretty much just leave this how it is. I haven't had much need to tweak it. It's it's only relating to how agents avoid each other and dynamic obstacles at runtime using the dynamic obstacle avoidance system. The higher quality the avoidance system, the better it's going to be. You can also assign a priority, so you can say that some agents have a much higher priority and therefore their avoidance is much more important. And then underneath that you just have a few generic properties. Now one of them is whether we want our agent to automatically traverse off-mesh links. Now we talked earlier on that off-mesh links allow us to connect disjoint portions of the nav mesh. So we gave an example, didn't we, of there being a ledge that you might want the agent to jump down. By default, with auto traverse off mesh links ticked, this will automatically happen. But the problem is with that is when the agent moves from one point of the nav mesh to another point of the nav mesh using an off mesh link, it's more of a teleportation. So if you want the agent to really kind of fall down a cliff or at least a very steep ledge, you often want to do something else in your game. You want to trigger like a falling or jumping animation. And when you turn off auto traverse off mesh links, the off mesh link will still be seen from a pathfinding perspective, but from a steering perspective, once the agent gets to the off mesh link, it will essentially notify you, and then it will allow you to take some action such as start a falling animation, and then you can then be in control of actually moving it down to the next off mesh link yourself. Auto repath is just a way for the agent, once for whatever reason, say it's lost a path, say it's heading into a room and everything's fine, and then all of a sudden the door closes and it can no longer get to the target. Is it just going to stand still, or should it try and find another path to get to that location? And then finally we have the area mask, and we talked a little bit in previous videos about how we can define different areas in the nav mesh, and this is just our way of assigning which areas can be traversed by which agent. So this agent, for example, if we didn't want it to be able to walk through water, we would just untick the water area. If we didn't want it to be able to jump, we could unclick the jump area, and then any areas where there are ledges with automatic off-mesh links generated, it wouldn't traverse those either, I think. Although I haven't really tested that out, so hey, we're going to find out, right, a little further down the road when we start implementing all of these various things. So that is our nav mesh agent set up, and it's all ready now for us to start adding a script to in the next lesson. And that script is going to essentially be talking to this nav mesh agent and telling it to plot new paths and things like that. So looking forward to it. I'll see you in the next video, guys. Bye bye.